We want to review a couple principles from Electrical Engineering 240. And we're going to do this by working through a problem, a class activity. So the two principles that we're going to be reviewing are superposition and phasers. So first of all, superposition. So in superposition, you can, if you have multiple voltage sources, you can solve the circuit for each voltage source independent and then add them together. And then for phasers, phasers are how you analyze AC circuits. And so in this case, you see we have a DC voltage source and an AC voltage source. So we can't, if they're going to have different frequencies, then they're going to have different phasers. So we have to use superposition to analyze them separate. So we're going to start by analyzing the DC voltage source. So in superposition, we turn off the other voltage source, so that one becomes a short, and we have a DC signal, and so this becomes an open. So let's draw what our circuit looks like. So we have 10 volts. We go over here. We have 50 kiloohms. We have 40 kiloohms. And we have our 3 kiloohms. Then we come over here, and this is our 300 ohm. And here is our dependent current source, which is 100 IB. IB is labeled right there, and we're trying to find the voltage here, which is V out. Okay, so here's our circuit that we're trying to solve. So the first thing we need to do is solve for IB. So we're going to come in here. If I know what the voltage is across my 3 kiloohm, then I can calculate what my IB is. So we're going to use node analysis, set this up as node V1. So doing node analysis, V1 over 40K plus V1 over 3K plus V1 minus 10 over 50K equals 0. So we solve this and we get V1 equals 0.5286. So then, now that we know what V1 is, now we just say, well, IB is equal to V1 over 3K, which is equal to 0.5286 divided by 3,000, which is equal to 1.76 times 10 to the minus 4. Okay, so now that we have that, let's go back over here so we have more room. And now what we're going to do is we're going to do a KVL around this loop through here and then V out to ground. So what we see here is that this 10 volts is going to be equal to the current drop across here. So we have that V out is 10 minus 300 times 100 IB, which is the current from my dependent current source. So this is equal to 10 minus 300 times 100 times 1.76 times 10 to the minus 4. So this has a V out equal to 4.7137. Okay, so that was our, let's write that up here. So this is our DC source. Okay, so now we are going to do our AC source. Now we're doing superposition for the AC source. So with our AC source, now our DC source, it gets turned off, and we're using our phasor. So our frequency omega is equal to 10 to the fifth, and our impedance of the capacitor is 1 over j omega c, which is equal to 1 over j 10 to the fifth times 10 to the minus 6, which is equal to minus j10. And our source is going to just be 1 millivolt. Okay, so let's look at what we have now. So here is my 1 millivolt. I have a capacitor which has an impedance of minus j10. This is 40 kiloohms. This is 3 kiloohms. 50 kiloohms. And then we come over here and we have our 300 ohms. We have our dependent current source, which is 100 IB. Connect all of these, and this is our IB. Okay, so when we shorted out that AC source, you see that I have a ground here on the bottom, and I also, following around, also have the ground here up at the top. So this 50 kiloohms is actually in parallel with the 40 kiloohms. And we can take and we can fold our circuit in half. So we can change our circuit to look like this. We're running out of room, so I'm going to have to move this over. And then you see that we have our dependent current source. So what we did is we took this point on our circuit, which is shorted to this point on our circuit, and then flipped them around. So this point here, which is V out, you see this point here is going from V out to ground, which is all the way over here. So you see this 300 ohm flipped down, the 50K flipped down, and then I have this circuit here. And then this is, if I can write it in here, this is my 100 IB is my source. Okay, so in order to get my IB, which is right here, again, I'm going to do a node analysis, and so there is my V1. And so now I have V1 over 40K. Plus V1 over 50K plus V1 over 3K plus V1 minus 10 to the minus 3 over minus J10 equals 0. So we can come in here, we solve this equation, and we get V1 equals 10 to the minus 3 plus J 3.78 times 10 to the minus 6. And so the first thing that we notice here is that this real part is basically almost 3 orders of magnitude larger than the imaginary part. So what's going to end up happening is that this imaginary part is going to become negligible. And so we see that V1 is approximately equal to 10 to the minus 3. So now we're going to plug in our IB, which is going to be equal to V1 over 3,000, which if we plug in the numbers and get it all exact, we get 3.33 times 10 to the minus 7 plus J 1.26 times 10 to the minus 9. And so this 10 to the minus 9 is going to become negligible. And so now our V out is going to be equal to minus 300 times 100 times IB. And so the V out is equal to minus 0.01 because the imaginary part becomes negligible. So now we have to convert, this is a phasor V out. To be exact, these would all be phasors. And so we want to convert it back into the time domain. So V out of t is equal to minus 0.01 cosine of 10 to the 5th t. Now we're going to take and we're going to add these together. And so now our total V out is equal to this, the 4.7 minus 0.01 cosine of 10 to the 5th t. And that is our answer. And so you see it has two parts. It has our DC part and our AC part. And because of superposition, we can just sum the two together.